This question introduces several concepts we're just going to want to make a note of. And again, it's going to ultimately come down to equation manipulation, but we're going to want to make a note of several different things going on here. So one is unit weight. Basically, when we're dealing with soil problems, you're often going to use the unit weight, pound force instead of pound mass, which is going to be gamma, and that's just your total weight over your total volume. So make a note of that. We're also going to be using the concept of dry density. Or dry unit weight. We're trying to understand the unit weight of the dry parts of the soil, not the total. So dry in this case is indicating the solid, since the air doesn't have any weight of its own. So that's another thing we're going to want to do. And lastly, we're going to want to make a note of the fact that a lot of these cut and fill type problems involve again the borough or the bank cubic yards, the loose cubic yards, and the compacted cubic yards, where there may be more water or air added to the soil, but the solids don't really change from state to state. They're basically the same amount. You may have added some air between, or some voids between, but you're not going to impact the weight of the soil. So it's going to be helpful for us then to make note of the relationship between those things. And so that's what you're going to see here. These are subscripts. This is just taking a similar equation up here and just equating the weight of the soils between the three states are equal, and so you end up with that sort of relationship there. So we have some given data here, again, like most problems that we're starting with. Then 112 unit weight here, 116. We have the water content for one and the other, actually. We also have a volume for one. So naturally, two-part question: how much material must be moved? That's a volume question. And what quantity of water will be needed to add? So starting with the first one, which really can just be solved from our dry unit weight equation. Another one, if you don't already have written down or memorized somewhere, you're going to want to, because once you know that relationship there, it's really just a simple plug and chug type problem. And I'm not going to go ahead and go through the proof of all these equations when I use them. Again, I would just ask you to familiarize yourselves with them, because you're going to need them no matter what when you go through these types of problems. So that's our first relationship we're going to want to take advantage of. The next one comes from this equation here. This is going to help us solve for the volume that must be moved. Now that we have that dry density of the borough, that's the B, we can solve for the volume of the borough, again using that relationship there. We know the compacted volume. We know the unit weight of the compacted. It's at 116. We just solved for the unit weight of the borough. Everything is going to end up in cubic feet. Let's get it in cubic yards. Just make a habit of dividing out by 27. 3 by 3 by 3, 27 feet in a cubic yard, cubic feet in a cubic yard. We can solve for that volume, and we can get 4,375 cubic yards. So that's the answer to the first part. You'll probably only have to stop there for most PE type questions. You might have a two-parter, but usually you're just going to have one. In this case we have two. Good practice to go ahead and do that. So we can go back to that unit weight equation again, looking back at this one here. This is information we're going to need here shortly for our next equation, which comes to us if you're following along in the construction specific workbook. It's equation 121, but volume of the water is equal to the weight of the solid, the compacted So we know this one now. We know both these were given. This is always 62.4. We can solve for what quantity of water will be required to compact the fill now. And that's fairly straightforward. So water contents, 62.4. Put that one to memory. And here's another one you're going to want to put to memory, or at least have it somewhere handy in case you don't trust your memory, and that's that each cubic foot of water is 7.48 gallons. Most books have this kind of somewhere in the front in the chart, and I definitely had to look back on it because I didn't trust myself, but it's a good number to have memorized as well once you plug and chug on this one. You can find that 41,715 gallons would have to be added in order to get to the optimal water content of 17%.